The first video for tutorial 2 is going to be on the topic of domain and range. Now, different people have different experiences with domain and range, so you might already know how to do all of this, and maybe you haven't seen it in a long time. So fast forward if you need to. But domain is the set of inputs found on the horizontal axis. So what I think of a domain is all the possible x values that a graph could have. So for example, if you look over here, this is a radical graph, which we'll be talking about in the next little section. But if you look at this graph, the graph is starting here at -4. And then how I think of domain is if I were to squish this graph onto the x-axis, or if I was to cast a shadow from this graph, where would it hit? And so you can see this pink line here is that the graph starts at -4, and then it has all the x values to the right. And this graph would extend to positive infinity in this direction and to negative infinity in this direction. So the domain of this graph is -4 with a square bracket to infinity with a round bracket. Now, if you are not comfortable with interval notation, which is what this is, you're going to want to go to your textbook and go to page 867 and do just-in-time number 6. So interval notation, it's a thing. Really, all you need to know is that if you're equal to the number, you use a square bracket. If you're not equal to the number, you use a round bracket. Infinity will always be a round bracket because you can't equal something that you don't know what it is, right? It's somewhere way out in the right-hand side. And then the range is the set of outputs, so your y-axis. So if I look at this graph, this blue line is showing you your possible y values. So your y values start here at 0, and then they continue up. And again, this graph is going to go up to positive infinity in this direction, and then it would go down to negative infinity in this direction. So what we're going to now do is determine whether the relation is a function, and we're going to identify the domain and the range. Now, before we start doing them on here, what I always like to kind of show is this PowerPoint. So I was talking about casting shadows, and I wanted to show you sort of what I meant by that. I just have to switch my pages, one sec. Okay, there we go, showing on the wrong screen. So here's an example of a graph. Now, again, we'll be covering this in a little bit, but this is an absolute value graph. And if I asked you what the domain is, you're looking for where this graph would squish onto the x-axis, or if you cast, shone a light from here, where would it cast a shadow onto the x-axis? Now this one, it has arrows to the left and it has arrows to the right, and there's graph all the way between it. So when I cast this onto the x-axis, it's covering everything from negative infinity to positive infinity. So your textbook would say x is all real numbers, which you could also show with a symbol, which I'll show you when we go back to the note, or you could use round brackets and go from negative infinity to infinity. Now, if we wanted to do the same thing, but for range, we're seeing where would the graph squish onto the y-axis. So if you took, two bookends and you just squish this graph on, you wouldn't have any graph that would squish down here. Whereas your graph would start at 2 and go to positive infinity. So watching the projection, your range would be y is greater than or equal to 2, that's your set notation, or square bracket 2 to infinity. Now, when I ask you domain and range, I don't care which one you give me. Your textbook, when I look at it, sometimes gives both, but mainly just gives interval notation. So do get used to this interval notation. Let's pick another one. Now this one, I always think it's funny they show because it's identical to the last one we did. So if you look at this graph, it's got arrows going to the left and to the right, and there's a continuous graph between it. So the domain is also all real numbers, or negative infinity to infinity. Again, set notation, interval notation. And if I went back and I showed you the range, again, if I squish it, there's going to be no graph below here. The graph will start at -2 and go to infinity. So you could say y is greater than or equal to -2, or you could say square bracket -2 to infinity. Just showing a couple more. This one, again, if you go for the domain, there's arrows going in either direction. So if I squished this on, you'd end up with all real numbers, or negative infinity to infinity. And if I go back and I do the range, this time it has arrows. Like on the other examples, both the arrows were pointing up. Whereas this one, I have one arrow pointing down and one arrow pointing up. So the range of this graph is also all real numbers, or negative infinity to infinity. Last graph I'm going to show you is this guy here. This is a radical graph. If you again squished, your x-axis would, or your x values would start squishing at -2, and they would go all the way along and keep going. So my domain is x is greater than or equal to -2, or square bracket -2 to infinity. And then again, if I looked at the range, it's going to start at -2. So it could be y is greater than or equal to -2, or square bracket -2 to infinity. So now I just really wanted to show that for the animations, but we're going to go back to the note and put some notes down. Okay, so let's try these. So let's look at these graphs. First thing we're going to do is determine domain. So when you look at this one, you're looking at where do you start getting x values? Now you've got a solid dot here, which would translate to 1, and then it goes all the way to this solid dot here. So my domain is going to be 1 to 5. Again, the textbook just shows interval notation, but if you do love set, like if you want to answer x is greater than or equal to 1 and less than or equal to 5, this is great too. This is called set notation, and this is interval notation. The range, what would we do? Well, if you look at the range, it's going to start here at 1, and then it casts shadows, or it squishes onto the graph all the way till 4. There's no arrows, so it's got a start and a finish. So this range would be 1 to 4. Or if you really like set notation, you could say that the y value is between 1 and 4. When we look at the next graph, again, we're going to start with domain. For this one, we've got our arrows. So this arrow is pointing to the left, and this arrow is pointing to the right. So there's graph between, but also extending all the way and extending all the way. So in interval notation, we'd say that this domain is -infinity to infinity. Now your textbook writes all real numbers, but anybody who's taken, math courses where they love set notation, you would write this as x is an element of, or a member of, the real number system. So you have two choices. Again, interval notation, set notation. Eventually I'll stop writing set notation when I've shown you a few and stick to just interval notation, but for something like that, people often switch to the set notation, and that's totally fine. The range, there are arrows, but they don't point down and point up. So this graph, it starts at 1 and it ends at 5, because these lines are not gradually increasing, they are going straight across. So for this one, the range would be 1 to 5. I almost put 4. It's very similar to the graph before, but just that little bit different. And again, the range would be everything from 1 to 5. Pause the video and try the next two. And also, actually before you try the next two, we forgot the first part. Determine whether the relation is a function. So what we would do is the vertical line test. Do I pass through more than one point? No. So this guy is a function. This guy, very similar, still drawing a vertical line, never passing through anything. This one is also a function. Okay, now pause the video and try these two. Okay, so for me, I'm going to stop doing set notation. I'll just do interval. This one goes from 1 to 5, and the range goes from 1 to 5 as well. What happens when I stick arrows on it is that my domain is now -infinity to infinity, or all real numbers, and my range starts here at 2, and then it extends and keeps going to infinity. So this would be 2 to infinity. I always have this moment where I'm like, oh, I just want to show set notation as well. This one, just in case, right? This one would be 1 to 5. This one would also be 1 to 5. Put to y. This one would be all real numbers, and this one would be y is greater than or equal to 2. And then in terms of function, vertical line test, these are both functions. All right, those are our kind of more 4 traditional graphs. Then I wanted to throw some tricks in you that are just going to help you with stuff coming up and sort of make you think about open circles really. So this first graph, if I were to ask you the domain of it, you should see that it's going to start at -2 and go all the way to 1, right? If you pressed onto the x-axis, this is where you would cast a shadow or make an ink print. But the difference between this graph and the other graphs we're doing is that these are open circles. Open circles mean that that point doesn't exist. You go up to it, but it doesn't exist. So the only difference with this one is that instead of square brackets, we would switch to round brackets. So my domain would go from -2 to 1. My range is going to start down here at -1. Now this is not an open circle. So you'd have a square bracket at the -1, and then it's going to go all the way up to 3 and have a round bracket. So my range would be -1 equal to, but then 3 not equal to. If you were writing these in interval notation or set notation, you would just take off the equal signs. So this would be x is greater than -2 and less than 1. This would be y is greater than or equal to -1 and less than 3. And again, I don't care which one you do. Now, as a function, it does pass the vertical line test. So this one is a function as well. What about this one? Right? You're welcome to pause the video at any point in time, but let's look at this guy. First off, let's answer the question of is this a function or not? If I draw a vertical line, pass, 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 the only point I'm questioning is here. See how, that came out kind of messy. If I look at x is equal to -1, we don't have a point here at -1, 1. But we do have a point here at -1, 2. So technically this graph only has one y value for that x value of -1 because of the open circle. And then everywhere else it passes the vertical line test. So this guy's a function. Now saying that, if we look at the domain of this function, I've got an arrow going to the left and I've got an arrow going to the right, and there's no gaps. So my domain would be -∞ to infinity, or all real numbers, or XER. And then my range, where does it start? Well, it starts down here at -3, and I get lots of overlap here at 1, but it just matters that there's a graph. So it's going to start down here at -3, and then it's got an arrow continuing up. So even though this one went to the left and stopped having y values, this part of the graph overtook it, and then I still have y values. So this range would be -3 to infinity. And again, you could write that as y is greater than or equal to -3 if you want. This is a weird one, and the reason I put this one on is because in a couple lessons we're going to be graphing these. And what these are, they're called piecewise functions, where there would be a piece of your graph that would be a straight line, and then there'd be another piece of your graph which is a curve. Okay, we will learn the names for these in a bit, but you'd have a constant and then a quadratic section. And you would be graphing this constant for any x value less than 1, and you'd be graphing this quadratic for any x value greater than or equal to -2. And so you get this overall function graph, but made up of pieces. But we're just looking at the overall domain of it right now. This next one I threw on because of this hole. What do we do when the graph is everything? Now, if you don't have arrows, if your graph reaches the end of a grid, it's assumed to go on forever. So this one actually does have arrows at the end. So if we look at the domain of this guy, it's everything to the left. So it's going down to -infinity, and it's going up to +infinity, but there's something happening at the 2. There is a hole at 2. So for interval notation, what we would say is that my graph goes from -infinity up to 2, and then it goes from 2 up to infinity. And that's how we show that there's a hole. So that's interval notation. And again, like I said, your textbook kind of switches between the two. If you look at the domain of this in set notation, again, they use the set brackets, and they would say it's the set of x such that, and again, this is just a form, not again, but this is a formal statement. So just so you know, when you're looking at your textbook, what they'll often do is anything in set notation, they put in set brackets, and they put this set of x such that x is any value greater than -2 and less than 1. So I'm just going to put set of x such that, and they would just put x cannot equal 2. And they'd call that the domain. So instead of saying what x is, which is anything from -infinity to 2 and anything from 2 to infinity, instead they say, hey, x can't be 2. What can it be? Everything else. And in a proper set notation, they would actually write that. They would say the set of x such that x cannot equal 2, but x can be everything else real. So this is the full sentence. To be honest, if you just put x cannot equal 2, I would give you full marks. The range, see if you can pause the video and figure out what the range would be. So for the range, you've got a hole at 3. So it would be negative infinity up to 3, and then 3 to infinity. Or in set notation, you could simply put x cannot equal 3. If you put the x such that, great. If you put the x as an element of the real number system, great, but this is also fine. Is this one a function? Well, vertical lines never passes through more than 1 point, so I would say that this is also a function. Awesome. So go and practice some domain and range questions in your textbook.